Welcome back everyone. In the last two lectures we had seen how to draw root locus for a closed loop system. What was root locus? Root locus was basically the locus or the collection of all the closed loop poles of the system when the variable k is varied from 0 to infinity. We came up with these rules, 7 or 8 rules, and then we use those rules to come up with the root locus. We will revisit that root locus problem that we had taken in the last class soon, but before that let us move into a very important part of any system theory, not just control theory, which is called stability. Any system, a robotic system or any other system that you take must be stable. Now, what is the meaning of stable? We must come up with a definition to explain what stability is. If a system is not stable, then the system will misbehave. It won't behave as you wish. It might get damaged as well. So, stability is a very important part of any system, be it a robotic system or any other system that we have. So, let us look into what stability really is. So, here is a closed loop system, unity negative feedback configuration closed loop system. Here you can consider that this is the actual closed loop system, this entire block, and the transfer function for that is this. And then I can ask the question, is this system stable? So, roughly speaking, stability implies that any small change in the system's input or initial condition should not change the output considerably. This is roughly speaking what stability means. However, till now I have not given a mathematical definition of what stability is. Now, to understand that, we have to go back to the idea of response of a system. If you remember, response of a system can be divided up into two parts: natural response of a system and forced response of a system, which were also called the zero input response and the zero state response. Let me jog your memory a bit. Zero input response is the response of the system due to initial conditions only, all inputs being 0, and zero state response was the response of a system due to input only, all initial conditions are 0. Now, stability of a system can be looked into from two perspectives. At least there are only two perspectives that I will discuss in this course. One of the perspective is from the case when there is no input to the system. Now, suppose if you have a system and you are not giving any input to the system, when can I say that the system is stable? Now, a linear time invariant system is stable if the natural response approaches 0 as time approaches infinity. So, right now I am talking about the zero input response case. So, I am considering there is no input to the system. Now, if then we say this, the LTI system is stable if the natural response approaches 0 as time approaches infinity. So, here is a plot where the response of the system goes to 0 as t tends to infinity. Whereas, if the natural response grows unbounded, here is a plot where the natural response of the system is unbounded, then we say that a system is unstable. Whereas, you can have a case when the natural response neither decays nor grows. It keeps it is either constant or it oscillates as time approaches infinity, and such cases we call them to be marginally stable. From these three definitions, you can be sure that, okay, what does stability in case of natural response means? The definition of stability implies that if you have the total response, which is natural response and forced response, if the system is stable, the natural response part must go to 0 as t tends to infinity. only the forced response will remain. So, this is what stability is from the perspective of natural response. So, suppose the natural response we can now neglect, suppose we look into the total response now. So, what would the meaning of stability from total response point of view? Now, you see, remember, now since we are looking into total response, we are also looking into inputs. So, see, you are given a system and you are asking whether this system is stable or not. Now, you give an input which itself is unbounded, which is increasing with time. Say it's a ramp input, right? The input itself is unbounded. The value of the input itself is increasing as t is increasing. So, the output will also increase, right? So, it is very unfair on the system if we say that, since your output is going to infinity, so the system is unstable. That is unfair on the system, because the input to start off with was unbounded. So, if you are giving an unbounded input and then you are getting an unbounded output, what do you mean unbounded? Means that at t tending to infinity, it is infinity. So, you are giving an unbounded input and then you are expecting that when it enters the system will manipulate this input to give you an output which is bounded. That is unfair on the system. Like, unfair word I should not use technically, but on the system it looks like unfair, right? Why will I call the system unstable? It is not the fault of the system. You are giving an input which is unbounded. So, hence we have to carefully define what is the meaning of stability for a system, when inputs are also taken into consideration. Initial condition is already there and now inputs are also there. So, a system is stable if every bounded input, this is very important, the word every, if every bounded input yields a bounded output. Okay, any bounded input you give, the output should be bounded. Then we say that the system is bounded input, bounded output, stable system. Remember, the word every is very important. So, what happens is people just go for, suppose I am asking whether this system is stable or not. You checked with a simple bounded input and then saw that the output is bounded. So, you are directly saying, no, the system is stable. No, that is not correct, because it may be for some other bounded input, output might not be bounded. Take this integrator. Now, in this integrator system, you can give 0 input to this system. What will be the output? The output will be 0. So, 0 is a bounded input, output you are getting bounded. So, does this mean that this system is BIBO stable? It turns out no. Okay, this is another example where I have given another bounded input. See, if I give this bounded input to the system, the output of this system is this, and this is a bounded output. So, I am giving a bounded input to the system, but the output is also bounded. Just by looking at this, you cannot infer BIBO stability, because if I give unit step as input to this integrator system, then I know that the integration of unit step will come out to be t of u step, which itself is an unbounded signal. So, this is an unbounded signal, right? But this is a bounded input, bounded signal. So, you came up with one example. If you just come up with one bounded signal that results in an unbounded output, you can directly say that the system is not BIBO stable. However, if you have to prove that a system is BIBO stable, you have to look for all the bounded inputs. Now, of course, you can understand, right? There are infinitely many bounded inputs to test. How is it possible to test whether for this infinitely many bounded inputs, the output will be bounded or not? So, it is not possible, right? Theoretically, although the definition says that, but we must come up with a easier way of checking whether a system is stable or not. And the easy way of checking is looking for the poles of the system. It turns out that the poles of the system will tell you whether a system is stable or not. Let us look at how this will happen. Let us take the transfer function of a system. Now, suppose you have a big transfer function, numerator is say 100 degrees, denominator is say 1000 degrees. So, you can always write down such a transfer function as partial fractions, where the partial fractions will be of the form n1 by d1 plus n2 by d2 and all, where d1 will have highest degree either 2 or 1, right. If it is a real root, then you will have a degree of 1, and if it is a complex root, then we will take then the polynomial, then the denominator polynomial will be of degree 2, because we are avoiding complex coefficients in the denominator, right. So, basically what I am trying to say is that if you have a plus jb and a minus jb as root, then you can always write a fraction of the form, this can always be a fraction, partial fraction term, and then something will be there in the numerator. Okay. Now, notice that if this is the case, now what will be the output of this? So, the output of this will be equal to say Ni by d1 into input suppose is r plus n2 by d2 into r plus dot 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 n4 by d4 into r, and it can keep on going. Now, if each of this term are bounded, then when you add them up, they will come up to be bounded. Okay. So, the point here being made is that if I just try to understand how one of this term behaves, I can understand for other terms also. In this case, what can happen is that suppose I take one of this term, now d1 can have roots on imaginary axis, it can have roots in the positive half of the complex plane, it can have roots on the negative half of the complex plane. Now, based on where the position of the pole is, we can directly comment whether the total response will lead to a bounded response or an unbounded response. So, for example, suppose you have left half poles. So, if you have left half poles, then the term, suppose I am taking an example here, suppose the transfer function or one of the partial fraction terms is this. Now, in that case ys will be this. Now, this can be written down as k by s plus 1 whole square plus 1 plus b by d. Now, you can find out yt. So, this should have been yt, this should have been yt because we are in time domain. So, yt is Laplace inverse of this term plus Laplace inverse of this term. Now, since Rs was bounded, this will turn out to be a bounded signal. When you do Laplace inverse of this rational function, you will get something in time domain. This will be some function, say f1t. So, f1t will be bounded because Rs was bounded to start off with, but this term is coming from this part, right. The denominator, this part is influencing this this first summand here, and you can see in the first summand when you do a Laplace transform, you will get a term of this form, and you can see that e to the power of minus t, here the exponent is nothing but the real part of the pole of this system. So, what are the poles of this system? Minus 1 plus minus j. So, the real part shows up as the exponent of e. Okay. And this as t tends to infinity, this term will go to 0, and since this was bounded, this will also go to 0. Okay. So, what I am trying to say here is that if the poles of the system are on the left half of the complex plane, then the system will turn out to be stable. It will give you a stable or a bounded output for any bounded input that you give. See, I had not put a specific bounded input here, I kept it general. So, if you give a bounded input, the output will come out to be bounded always if the poles of the system are on the left half plane. And the reason for that is this, now see, if the poles are on the left half plane, if you find out the roots of this, it will be a plus jb, and the real part of a will be less than 0, and the solution or the response will have a term of the form e to the power of at into some term. This e to the power of at term dies to 0 because a is a negative number here, and it will go down to 0 as t tends to infinity, taking this entire term as a whole to 0. See, I am not going into rigorous proof of stability. I mean, there are ways to prove these things, okay, but I am not going into those rigorous proofs. I am just giving you the intuition. So, the intuition here is that since the real part of the pole is on the left half plane, you will have in the final response or the output response or the output of the system, the expression that you will get will have an e to the power of exponent term multiplied by t, where that exponent a will be negative, and that is the reason it will the final response will die down to 0 as t tends to infinity. Whereas, if you have something on the right half plane, then this will be something like this. Now, in this case the location is this 1 plus minus j, and so now you can see the exponent is e to the power of t here, because the real part is 1. So, it will be e to the power of 1 e to the power of t, and that will blow up as t tends to infinity. What happens if poles are on the imaginary axis? If there are poles on the imaginary axis, suppose there is a simple pole on the imaginary axis. What do you mean by simple pole on the imaginary axis? That means there is only one pole at a point. So, suppose there is only one pole at say plus j2, and then the other will come at minus j2. Okay. Now, if there were two poles at the same location, we will look into that after this, but right now we are calling it to be a simple pole. Simple pole means at a point on the imaginary axis there is only one pole. Now, so 10s by, so of course this can also happen. So, suppose this is plus 3 and minus 3. So, these two are also poles. Now, here plus j3 is also simple, minus j3 is also simple, minus j2 and plus j2 are also simple, because they are not repeated more than once. Okay. So, here you can see this is the example where I have taken 10s by s square plus 4. So, plus minus j2 are the poles in this case for this system, and if you go ahead and find out the response of this system, you can see I can do the same thing. So, response will come out. We will see what the response is. I have taken a simple example here. Now, I have taken Rs to be some sine of 2t, and let us see what will be the output like. If I take sine of 2t, then you see Rs becomes, since Rt is equal to sine of 2t, Rs is 2 by s square plus 4. So, this expression will become 10s by s square plus 4 whole square, and if you find out the Laplace inverse of this will come out to be 5 by 2 t sine of 2t. Okay. And you can see that the output in this case is unbounded, because there is a t sitting over here. As t tends to infinity, t goes to infinity, right. So, this is an unbounded output, and the input that you gave was a sinusoidal signal. We know that it will be bounded, right, it will be bounded. So, which means that for a bounded input you are getting an unbounded output. That means this is not a bibostable system. Understood? But there is something important here to note, that if you take, instead of sine of 2t, if you would have taken sine of 3t, then your Rs would come out to be 3 by s square plus 9, and in that case if you go ahead and find out the yt will come out to be 6 cos of 2t minus 6 cos of 3t. Now, notice this was also a bounded input and you are getting a bounded output. So, the point that I am trying to make here is that although this system is not bibostable, because I have found out a bounded input which resulted in an unbounded output, it turns out there can be inputs for which the output is bounded. Okay. Actually, what happens is you should be able to guess this, that why was this t coming in the expression? Because the denominator here became s square plus 4 whole square, which means there will be a t coming in the final expression. However, if the denominator did not become square, then this t will not show up in the final expression, which was the case here. Okay. Here you could say this was s square plus 4 and this was s square plus 9. So, in that case I could do a partial fraction and the t never came up in the final expression. So, the t was the problem, right, because of this t the output was getting unbounded. So, the idea here is that you can write 10s by s square plus 4 as s square plus 2 square, right. So, the natural frequency here is 2. So, if you take a sinusoidal signal which has a frequency of 2 radian per second, then the output will become unbounded. Whereas, although here the natural frequency was 2, I took a different, the input that I took was sine of 3t, which is not, the frequency in this case is 3 radian per second and not 2 radian per second, and that is the reason the output came out to be bounded. So, if you have a system of the form a by s square plus b square, then if you give sine of bt as input to it, then the output will become unbounded, because the input frequency is matching the natural frequency of the system. Whereas, if you give suppose sine of gamma t, where gamma is not equal to b, then the output will not become unbounded. So, these type of systems are called marginally stable systems, because these are some specific kind of inputs that you can create, for which the bounded inputs you can create, for which the output becomes unbounded, not for all bounded inputs. Most of the bounded inputs will work well only there if you can avoid this specific kind of bounded inputs, which actually matches the natural frequency of the system. If you can avoid those sinusoidal signals, then you will be fine. Okay, and these type of systems are hence called marginally stable system. Remember, these are not stable systems, these are unstable systems, but we can use these systems, because we can come up with inputs for which the output will remain bounded. Now, if there are repeated poles, so what is the repeated poles case? Suppose there are two poles now, plus 2j at the same point, there are two poles, okay, on the imaginary axis. Then whatever bounded input you give, you will get an unbounded output, because now you see the s square plus 4 whole square term is coming in the transfer function itself. So, when you do a Laplace inverse, t will come, right. So, that is the reason. Whatever RS you choose does not matter. Of course, if RS is 0, it will come out to be 0, but when I mean whatever RS you choose, I think you understand that any other bounded input if you take, because of this s square plus 4, when you do a partial fraction, you will always end up in a term which has t in it. Okay. So, as a whole, if all the poles are on the left half of the complex plane, then the natural response of the system will decay to 0 exponentially. So, and what will be the BIBO status? Basically, when I look at the system, if by taking input into consideration, then we will call that the system is stable. Such a system is called a stable system. If there are simple, which is non-repeated poles on the imaginary axis and no right half plane poles, okay, there should not be right half plane poles, then there will be sustained oscillations or constant value of the natural response. Whereas the BIBO stable, is it BIBO stable? No. So, it is an unstable system, okay, and we call these type of systems as marginally stable. So, it can have imaginary axis poles, okay, but it should not have poles on the right half plane, because as soon as a pole is there on the right half plane, then you see any pole in the right half plane or repeated poles on the imaginary axis, unbounded response of the natural response, system is unstable, and this is not BIBO stable as well. You have to remember this idea that, okay, now you see I do not have to check for every bounded input, I just have to remember where the pole locations are. If all the poles are on the left half plane, I am safe, I know that the system will be stable. However, if at least even if one pole goes to the right half plane, system is unstable. If two poles are on the imaginary axis at the same point, system is unstable. So, you have to understand all these subtleties, and that is what stability is all about. Next, what we will do is we will use these ideas and we will try to see where are the poles of how can I find out the location of the poles of a system without even calculating the roots, because calculating the roots of a big polynomial, say of 100 other polynomial, will be very difficult. There is an easy way of finding out the location of the poles, because you see it is only the location of the poles that matters to find out whether a system is stable or not. I do not need the exact value of the poles. Okay. So, the location of the poles will be very important. Remember, however, for controller design I need the exact value of the poles, because exact value of the poles will give you the specifications. Okay. But for knowing about stability, I do not need the exact value of the poles. I just need to know if all the poles are on the left half or not. If all the poles are on the left half, I know that I am safe and the system will be stable. And when I am talking about all the poles on the left half, I am talking about all the poles of the closed loop system, not the open loop system. The open loop system, to start off with, can be a unstable system. So, for example, if I take, for example, the quadrotor example, if you remember that the transfer function was 1 by s square. So, to start off with, is this a stable system? Now, in this case, two poles are on the origin at the same point on the imaginary axis. So, this is a unstable system. This is not BIBO stable. So, now if I take this system and I put a system like this, where I have put a transfer function, put a controller of this form, say now what is the transfer function of this new system. I have added these extra things and the new system now becomes k by s square plus k. You can check, this will be the transfer function of the new system. So, this is the new system, the transfer function is this. Now, if I ask you, is this system stable? Again, where are the poles? Poles are at plus minus j root k. So, is this system stable? No, this is not a BIBO stable system because the closed loop poles are on the imaginary axis. However, it is a marginally stable system because if I can avoid some specific inputs, then I would be able to get an bounded output. So, that means that I can also add something else here and try to make the system stable. So, this is the way by which we can conclude about the closed loop system's stability. Okay, and it is the locations that matter more for stability than the exact value of the pole, and in the next lecture we will see how to find out the location of those poles. Thank you.